Cool. We have more than 1,000 people here, so it's probably good to get started. Amir will be teaching the second of the quantum mechanics series today, so I'll let him describe that. But just really quickly, while people join, a reminder that every week there's a homework assignment due. It's graded just for completion. It's graded for accuracy, but you can submit unlimited times, so you can continue to submit until you get the score that you're comfortable with. But just a reminder, that's due Sundays at 11:59 p.m. Eastern time zone. So it's not too late to get your homework done for this past week, and the assignment for next week is already posted as well. So please make sure you get your homework done. Please also make sure that you're attending lab. Again, attendance for lab is required. We have a flexible attendance policy. We know that life happens, so don't worry too much about that, but do make it a habit to attend your lab section, and you can read the student handbook for additional details on those policies. And I think that's it for announcements today. I will turn it over to Amir to take us through the lecture.
Hi, everyone. Welcome to the second day of our quantum mechanics lecture series. Today, we'll be talking about two-level systems and measurements. And the objective that we're trying to accomplish here is that, first of all, what are two-level systems? What do we mean when we say a two-level system in physics? And what can we do with them? And actually, for that matter, why do we care about them? So we'll be talking about, again, two-level systems, the Stern-Gerlach experiment, or Stern-Gerlach, which is a famous physics experiment that talks about how do we know electron spin is a two-level system. It helps us determine that. Next, we talk about quantum measurements, again, using the tools that we've developed by talking about the Stern-Gerlach experiment. And specifically, we want to talk about how do we measure a two-level system in different bases. You might have heard this term so far, but we're going to try to give you guys an actual intuitive picture of it today. And finally, we're going to talk about quantum entanglement, which is a property that quantum systems, specifically two-level systems that we care about, exhibit. Okay, with that, again, let's go back to a reminder of quantum systems. So what we discussed during the last lecture was that the quantum world happens to be discrete, unlike the classical world around us where we observe things to be continuous. So a good picture that the teaching team really likes is the example of stairs versus a slide. So when you're going downstairs, you can only step at one stair at a time, so it can only be at discrete heights from the ground. Whereas when you're going down a slide, there's a continuum of different heights from the ground that you can be at. So with that, let's talk about two-level systems. So a two-level system is a quantum system made out of two bases. And in other words, if I measure the quantum system, I can only get two possible measurement outcomes. So an example of a two-level system is a qubit, of course, that we talked about. You can, after you measure a qubit, you can only have two possible values, 0 and 1. So that's a two-level system. Another example that some of you might be familiar with is an electron spin. So spin is a property of electron and comes from an inherent magnetic moment, essentially. And it can either be pointing up or down in the presence of a magnetic field. So let's see an example. Again, two-level systems, qubits an example, and they can be in a superposition of two different states, 0 and 1 in this case. And after we measure a two-level system, we either get 0 or 1, with some probability that we're going to talk about later. But we only have two possible measurement outcomes. Now, we could also have a three-level system, just to give you guys an overview of what that would be like. So a three-level system is made out of three bases, again, meaning that if we measure this three-level system, there are three possible outcomes that we can get. In this case, the possible outcomes are 0, 1, and 2. And a three-level system in the context of quantum computing is sometimes, or actually it's a lot of the times referred to as a Q-trit. And this trit comes from 3. So bit came from binary, meaning two possible values. Trit comes from, again, the fact that this system can have three possible values once you measure it. Okay, so before we get into the details, why do we use two-level systems for quantum computing? Well, first of all, we can map one level to 0 and another level to 1, and that makes it analogous to the classical computers that we're accustomed to using. And the second reason, actually, this is more of a quantum hardware engineering and a practical reason, is that two-level systems are easier to control than, let's say, three-level systems or four-level systems. And of course, they follow some simple linear algebra properties. We know the Pauli matrices, what they are, and we exactly know what the linear algebra properties that we need are for talking about qubits or two-level systems. And finally, they've been studied for nearly a century, almost since the invention of quantum mechanics. People have been interested in two-level systems. So now the question that I want to pose to you guys is, how do we know that an electron spin is a two-level system? And the way that we can probe that is using the Stern-Gerlach experiment, which is as follows. So we start, and hope to get this right, yeah. So we start by having two magnets on top and bottom. The top magnet is, let's say, the south pole of the magnet, and then the bottom one is the north pole. And we send a magnet through such that initially the north pole is facing up and the south pole is facing down. So in this case, what do we expect to happen? Okay. Try this. So we expect, and I see that the screen over there is frozen. Here we go. Amazing. Okay, I think we're good now. So something that we expect is that the north pole of our apparatus, again, the two magnets that we have here, will attract the south pole of the magnet that we're sending through, and vice versa. So such that, again, if this is the north pole of the magnet we're sending through and this is south, the magnet gets attracted upwards. This is intuitive. Again, the north pole of a magnet attracts the south pole of another magnet. Okay, now we'll send another magnet through, this time in the horizontal direction. Instead of having the magnet be aligned with the magnetic field of the apparatus, we send it perpendicular. And in that case, nothing's attracted and nothing's repelled. So the piece of magnet goes straight through if it's exactly perpendicular to the direction of the magnetic field of the Stern-Gerlach apparatus. Okay, let's do this again. And next, we turn our magnet upside down, and what we observe is that it goes down. If the north pole is pointing down, then the magnetic field here will pull it down, essentially. And now the idea is that we can send magnets with all sorts of different angles, and they will end up in a continuum somewhere from all the way up here to all the way down where the direction of the magnet is like the exact opposite. So, and this is what we expect based on the classical world. Again, based on what angle the magnets that are going through this magnetic field are, they're gonna experience different amounts of force, and based on that, they're gonna go up or down by a certain amount.
Amir, could I ask a quick question? Because I'm getting a couple of questions from the chat. Why are the magnets shaped in this weird way?
What do you mean by shaped? Like which magnets?
The Stern-Gerlach magnets.
So that is to ensure that, let me maybe draw a cross section. So if let's say this is the south, this is the north. We want to make sure that we have a magnetic field that goes in this direction. Now, the reason for this shape is to make sure that the magnetic field is perpendicular at all times, rather than going something like this, which would happen if we had just straight bars for the magnets. So it's just a matter of making the experiment work, essentially.
Cool, thanks.
Sure, that was a great question. Thanks, Akshay. Okay, so now let's replace our classical magnets with a quantum spin, which again, we said that had some magnetic properties, so we can go up or down. Okay, so if I send, a single spin, quantum spin in a superposition, again, I don't know the state of the spin before it goes in the, through this apparatus, so it could be pointing up or down. I don't know that. Okay, I send the first one in, it goes all the way up. Cool. And that's a repeat. Now I send the second one in, I see that it goes all the way down. So I keep on sending more and more quantum magnets or quantum spins through. And something that I observe is that they either go all the way up or all the way down. And this is unlike the classical example that we saw earlier, where again, depending on what angle the classical magnets were at, they would end up somewhere between up or down. In this case, what we're seeing is that when we send the quantum spins through this Stern-Gerlach magnet that we have, the magnetic field that we have, there are only two possible values that this spin can have. And this is, again, just to recap it. So instead of showing a continuum, we are seeing that the values are discrete. And the discreteness of the position comes based on whether the spin is pointing up or the spin is pointing down. So if the spin is pointing up, then up or down is something that we can decide as a convention. The quantum spin gets attracted upwards, it gets pulled up by the magnet, whereas if the spin is pointing down, then the quantum spin gets pulled down by the magnet. And the act of sending these spins through the magnet is effectively, in a sense, like measuring them. So after we measure the state of our quantum spin, there are only two possible values that we get. And this is, again, completely different than what we expect from the classical example of the magnets that we discussed earlier. Okay, so let's move on. I think I'm noticing that there's a very large delay between my slides, what I have on my iPad and what I'm seeing on the screen. So maybe let's okay, I think it's caught up finally. What does measurement of, it's completely out of sync now. So what does the measurement of electron spin look like in different bases? And again, we can think of measurement in bases, as the Stern-Gerlach magnet, essentially, where, you say you have this like magnetic apparatus and you send a spin through. And you can actually, this thing is is a special thing. So you can have it aligned either along, let's say, the z-axis, the x-axis, or the y-axis. And you can measure the spin of an electron along different axes, or what we call, in different bases. So as a review, and okay, maybe I will stop sharing and start sharing again, because this is just too annoying. Okay, hopefully the lag issue will be resolved now. And just as a review, what we mean by basis is essentially, this X and Y axes, like those form a basis. So, for example, if I have a point here, I can write this point as, so it's a 3 along the X axis and a 1 along the Y axis. So I can show the point essentially as a combination of my X axis, like how many steps I have to go along the X axis and how many steps I have to go along the Y axis. Now, I'm not just limited in having in a sense, upright basis, right? I can rotate things around and get a set of bases that looks like what we have here. And like, similar case here, right? I can show any point based on this new X prime and Y prime axes. So in this case, the point that I'm looking at here is 2, 1. And the idea is that any point that I can show using this set of bases or that axis, I can also show in this new coordinate system. I just have to, solve for some X and Y values, but it's fairly straightforward. Okay, so now again, let's go back to the Stern-Gerlach experiment. So, yeah. Sorry.
Before we jump into Stern-Gerlach, can you help? We're getting questions around just like what is spin. So in addition to reviewing basis, help us understand that.
Yeah, so that's a good question. That's a very deep question, actually. So you can think of spin as an inherent magnetic moment of an electron. In this case, what we're talking about, and the thing that really matters about spin is that it can either be, it can only be pointing up or down when you look at it. So it's discrete rather than being continuous like a magnet. And that is the analogy that I was trying to draw with the videos that now I realize were like kind of laggy, so might have not synced up with the explanations as well necessarily. But yeah, the distinction that I was trying to draw between classical magnets and these quantum spin magnets, quote unquote, is that classical magnets can be in any orientation that they want. And based on that, when we send them through this magnetic field, based on what orientation they're in, they're going to end up somewhere between all the way up and all the way down in a continuum, essentially. Whereas quantum spin is discrete. So when we send it through this magnetic field, it will either go all the way up or all the way down, and nowhere in between. And that kind of gives rise to the idea of a two-level system, because sending a spin through a magnetic field is essentially like measuring the spin in a sense. And once we measure the spin, quote unquote, we either see that it's pointing up or down always, and nothing in between. And that makes it a two-level system. So that's a key takeaway point. Okay, so let's revisit the Stern-Gerlach experiment now. This time without video, so hopefully lag would not be an issue. So let's have a bunch of quantum spins again. These are or two-level systems, if you like. Let's say two-level magnetic systems, so they react to the magnetic field. And I send them through this magnetic field that we have. And the magnetic field points from the South Pole to the North Pole. And let's see what happens. Actually, it technically goes the other way. It points from the North Pole to the South Pole. But that's just a convention. You can define it either, whichever way you like. And after I send these spins through, what I end up with is, they either end up all the way up or all the way down. So I'm going to call the case all the way up, spin up, as I'm, indicating here. And, we can say that is the equivalent of the zero state, the qubit having a zero value, or they go all the way, so they go either all the way up or all the way down. And we're going to denote that with this down arrow, or we can call it the one state. And since this magnet is oriented along the z-axis. Let's assume it's along the z direction. We call this measuring in the z basis. So again, this should be pretty straightforward because the electron lines up along the z direction. And that's why it's called measuring along the z basis. And I mean, what is special, again, for quantum spins versus just classical magnets is that you can only have two possible values, either all the way up, or which we call spin up, or all the way down, which we call spin down, and nothing in between. Okay, so let's now use the tools that we have to talk about how the Stern-Gerlach experiment relates to qubits and to quantum computing. So why do we care about this? So hopefully this part of the slide should be a review. The idea is that, let's say we have a qubit that is in state psi, which is alpha times the 0 state plus beta times the 1 state. And once we measure this qubit, we collapse the quantum state of psi, again, the superposition that psi is in of 0 and 1, to either 0 or 1. So this should be similar to the Stern-Gerlach experiment, right? Because what we saw with that experiment is, when we have this spin that's in a superposition, after we send it through our measurement apparatus, it either always ends up as up, which we call it 0, or down, which we call it 1. And based on this, based on the qubit state here, based on the superposition, we can calculate the probability of measuring 0 to be the magnitude of alpha squared. And just as a reminder, in this case, the probability, I'm going to call this P of 0, is equal to the overlap of the 0 state with psi squared. So if we want to, again, do this as an example here, I'll keep the magnitude squared here. I have 0 overlap with alpha 0 plus beta 1. And again, magnitude stays. I'm going to have alpha 0 overlap with 0. Just remember, the inner product or the overlap, again, from the first semester is a linear process. So similar to multiplying variables, essentially, this 0 out here acts on the 0 kit and the 1 kit separately. So I can write this as, okay, alpha overlap of 0, 0, or bracket 0, 0, and beta bracket 0, 1 squared. And again, if you remember from the first semester, we discussed how the overlap of the 0 state and the 1 state is 0. They're orthogonal or orthonormal. They don't overlap with one another. And the overlap of the 0 state with itself is 1. So we end up with alpha squared for the probability of measuring 0. And the probability of measuring a 1 state after we measure the qubit is beta squared. And is similar process. I'm going to write it down again as exercise, but it's a similar deal. So here we're looking at the overlap between 1 and the state psi squared. That gives me the probability of getting a 1. Again, I'm going to expand it the same way that I did for the previous case. So we have, except for that, this is 1 now, of course, not 0. We have a bra of 1 acting on alpha 0 plus beta 1. And this is squared. And of course, that gives me alpha 1, 0 plus beta times bracket 1, 1. Maybe let me make this a little bit more clear so we don't mix the bracket up with the 1 state, the ones that I'm writing inside. Squared. So this is equal to 1. And this part, the overlap of 1 and 0 is also 0. So what I end up with is beta squared. And again, this is similar to what we've seen multiple times the previous semester. And we're going to, again, reintroduce this next lecture in the context of the postulates of quantum mechanics. But the idea is that if I have a quantum state and I measure it, I get, again, if it's a two-level system, like a qubit or an electron spin, I end up with two possible values. And based on the superposition, based on the state, I can determine what the probability of getting each of those values are. And sending a quantum spin through a Stern-Gerlach experiment is similar to measuring the state of a qubit. So just to recap, measurement of a quantum system collapses it to one state. So if before the measurement we were in a superposition, here it is psi is equal to alpha times the 0 state plus beta times the 1 state. After the measurement, we either end up in the 0 state or the 1 state, and nothing in between. And again, that is the thing that's different between classical mechanics and quantum mechanics. Because in the classical world, you could end up in any continuous value between 0 and 1, whereas in quantum mechanics, you either end up in 0 or end up in 1, and nothing in between. So that's why we say quantum mechanics is discrete in nature, whereas the classical world, we perceive it to be continuous at least. Okay, so now let's think about measuring in other bases. So now I rotate my magnets by 90 degrees, and now I have them aligned along the x direction instead of the z direction that I was aligned along before. So in this case, what do I expect? Well, it's almost a similar story, right? Except for that I just have to rotate my head by 90 degrees. So in this case, the spins either end up to the right or to the left, still along the z basis, sorry, still along the x basis. So the takeaway message here so far is that my spins, after I send them through these Stern-Gerlach magnets, always end up along the direction of the magnets. Now, in this case, if they end up, if they end up going to the right side, we call them the plus state, or again, spin up in the x basis. Well, we're just going to denote that as the plus state. And if they end up going to the left, we denote that as the minus state. So now the electrons would, again, go to the two different sides, except for that instead of going up or down, like when the magnets were aligned along the z basis, now they go left and right. And we show that as the plus and minus states. Now, if you remember, this plus and minus state is notation that you might have seen before. Actually, you definitely have seen before in the first semester. And we're going to discuss exactly how it's going to come back. But okay, now let's say I sent some spins through this measurement apparatus that are aligned, oops, sorry, don't want to spoil the fun, that are aligned upwards along the z basis. So by the 0 state here, I mean upwards along z. And what I end up seeing after the spins go through is that I still get 50% going left, 50% going right. And that in a sense makes sense, because measuring the value of a spin along, let's say, the z-axis doesn't give me any information about what the value of that spin is along the z basis or the z direction. And if I send one through, again, the one state or spin pointing downwards, or just down along the z basis, I still see that my spins go right half the time and left half the time. Yeah, because same explanation that I gave on the previous slide. And now here, based on this, it's suggestive that we can show this 0 and 1 state that we have as a combination, sorry, this plus and minus state that we have over there as a combination of the 0 and minus state that we talked about earlier. We're going to see how, but for now, let's move on. So actually, maybe if we could use the polls for this slide, that would be amazing. So let's say I have a source of spin that is completely random. It's in a complete superposition, right? And I send it through, okay, here I have SG z-axis means that I measure along the z, and SG x-axis means that my magnets are aligned along the x-axis. So I'm measuring along the x-axis. So let's say I send my spins through the, the Stern-Gerlach magnets or apparatus along the z-axis. What do I get as a result for the output? So we know that there are two possible values for the output, but if you could have a poll on that, that would be amazing. So, so do I get up with 100%, down with 100%, or up or down with 50-50% probability? I realized I had to launch the poll. Okay, so far the majority are saying 50-50. Okay, I think it's conclusive. So 50% the upline and 50% the downline. Okay, now what I do is that I block the cases where the spin goes down. So I just add a block here, and I send all the up spins, all the spins that were pointing up along the z direction, to another Stern-Gerlach apparatus. This time I'm going to measure along the along the x basis, because I want to do that. So this is the x-axis. And again, I would get two possible outcomes. I'm going to call, so I'm going to relaunch the poll, but in this case, assume up is right. So for this, or up is the plus state and down is the minus state in the next poll. And tell me if, like after I measure, so so what I get is that I send the zero state, or up in the z basis, through to be measured along the x-axis. What do I get in that case? Again, remember that it's a different axis. So although I know the spin value along, what the value is along the z-axis, I have no idea what the value is along the x-axis. Okay, so based on what I'm seeing for the poll results, the majority of you, although not as dominant of a majority anymore, say again, 50% we end up in the plus state, 50% we end up in the minus state. And again, that in a sense makes sense, because so far, we first measured the spin value along one axis. We got one value, but that we don't have any information for what the spin value is going to be based on that measurement along a different basis or different axis. So when we measure the spin along that different axis, it could still be 50% left, 50% right, or 50% plus, 50% minus. Okay, so now let's say I again block one of these outputs, and send the other one through to another Stern-Gerlach apparatus. This time, aligned along the x-axis again. And now the question I want to ask you is, and I'm going to launch the poll again, what do I get for the spin value? Again, to recap the story, we first started by measuring along z. We got a 0. Then we measured along x, and let's say we got a plus state, or another up, and then I sent it through to another z. So what do I expect the value for that second measurement to be? Like if I measure z again after measuring x, what do I expect to get? Again, remember, when we first measured z, we blocked all the z values that were going down to 1. So yeah, what's the verdict? Oh, this is a close one. So I'll give it a little bit more time so everyone can vote. Okay, I think that's pretty good. So the results are actually very close for it being up 100% of the time, or 50-50 up and down. And actually the right answer is that it will go up with 50% probability and down with 50% probability. And this is very surprising, right? Because earlier we measured the spin value along the z-axis, and we blocked everything that was going down. So once we look at the spin value again along the z-axis, like what our classical brains expect is that it should still be up. But now the interesting thing is that now by the virtue of measuring along the x-axis, having this x measurement here, all of a sudden we have no idea what the z value is anymore. So let me draw a classical analogy to again emphasize how counterintuitive this is, what we just saw. So let's assume that an object has two properties, color and shape. If you want to map it to quantum spins, let's say color is spin along z, shape is spin along x, but that doesn't matter. So the color can be red or blue, and the shape can be square or circle. So, I have this object that I don't know what it is. It's completely random right now. I first measure the shape, and I get circle with 50% probability, let's say, and square with 50% probability. I don't know if 50% here is missing. Then after measuring the shape of an object, I toss everything that was a square. I block it, and then I measure the color of this object. And again, with the color, I get, let's say blue with 50% probability, red with 50% probability. And I block the cases where the object's blue. So I toss away all the blue objects. So at this point, classically or intuitively, what we expect is that we're only left with red circles, right? Because in the first step, we tossed all the squares. And in the second step, we tossed all the blue colored objects. But now if I measure the shape again, what I see in the quantum mechanical world is that I get circle with 50% probability and square with 50% probability. So just by the virtue of measuring the color of our object, I've lost all information about its shape. And if you're not surprised by that, then yeah, I'm surprised. I remember when I was first learning about this. This is very mind-blowing. Again, it's something that happens because of quantum mechanics. It's not a property that we see in the classical world, because again, in the classical world, we can see the color and the shape of things at the same time. And me, looking at the color of something doesn't change its shape. But what we're seeing in the quantum world, and again, taking this back to the Sturm-Gerlach experiment, is that when I measure the spin along one axis, and then I measure the spin along another axis, I lose all information about the spin along the first axis that I measured. And that is fascinating. That's very counterintuitive. But now let's use the tools that we have and we've developed in the class so far to try to explain this using quantum mechanics. So, let's say we start with a qubit in the 0 state, and now we want to measure along the x basis. So again, a qubit is analog to a spin. It's entirely the same math and physics. So when we measure in the x basis, which is again, it's like having our magnets for the Sturm-Gerlach experiment aligned along the x basis, it collapses the quantum state of the qubit psi to either the plus state or the minus state. And as a reminder, the plus state is an equal superposition of 0 and 1, the 0 state and the 1 state, and so is the minus state. The only difference is the sign between the two. And from those of you who remember this from the first semester, the plus state is a Hadamard applied to 0. The minus state is a Hadamard gate applied to the 1 state. And if you don't remember this, don't worry about it. We're going to see this over and over and over again. You'll become very comfortable with it by the time we're done with quantum computing. Okay, so now the idea is that I have, now this quantum state psi, and I want to measure it along not the z basis, not the usual 0, 1 basis that I'm used to, but along the x basis, which has the outcome either plus or minus state. Okay, so what is the probability of measuring plus in this case? Again, if you remember, so what we're doing here is going to be the same, the same method for getting the probability of measuring something along any arbitrary basis, or between any two arbitrary states. So the probability of measuring a plus, again, is going to be the overlap of plus with psi squared, well, magnitude squared. And if I were to write this out, so I have my plus state here, and then my psi is the 0 state here, right? And again, let me write the plus state now in terms of the 0 ones that we're comfortable with the properties. So I'm going to, actually, no, I won't do that yet. It's going to skip a math step, but I decided against it. Okay, so plus, oops, actually I should fix that. So bra plus is going to be bra 0 plus bra 1 divided by square root of 2. And then we're taking the overlap of this with the 0 state squared. And if I were to write this out, I'm going to move this square root of 2 out of my absolute value squared. So that becomes a 1/2. And I'm going to end up with the overlap of 0 with 0 plus the overlap of 1 with 0. And again, if you guys remember, this is 0, this is 1. So what I end up with is 1/2. And now let's look at the probability of measuring a minus when I send that qubit safe through. Again, it's the same deal. I can give you any basis, with what the possible outcomes are, and for any state, you can tell me what the probability of measuring that state is by looking the overlap squared of that state with the quantum state that you're trying to measure with the outcome state. So the outcome state here is a minus state, and the quantum state is just a 0 state. So here I have the overlap of minus with 0 squared. And again, I'm going to write out what the minus is in terms of the 0 and 1 state that we're used to. So here this is 0, in this case, minus 1 divided by square root of 2. And we're looking at the overlap of that with 0, which is the state psi. And same deal, I'm gonna pull this 1 divided by square root of 2 out of my magnitude squared, which gives me 1/2. And I end up with the overlap of 0 with 0. In this case now, minus the overlap of 1 with 0 squared. And yep, this is 0, this is 1, and 1 minus 0 is just 1. So I end up with 1/2 again. So this should make sense so far, and it's compatible with what we told you, that if I have, again, going back to the Stern-Gerlach experiment, if I have a spin that's pointing up in the z direction, which I'm going to call a zero state, and I extend it through my Stern-Gerlach apparatus aligned along the x-axis, what I end up with is half the times going left, half the times going right, to the plus or the minus state. Okay, so let's go back to the weird experiment that we talked about earlier. So just as a recap, here we have, we're sending psi, which is in superposition, through a z measurement first, right? And z-axis. And the two possible outcomes in this case are 0 with 50% probability, and so I'm going to write maybe, let's make this a little bit longer, 0 with 50%, and 1 with 50% probability. Now I block all the 1 states and I toss them essentially, and I send these 0 states now through a through another Stern-Gerlach measurement, this time along the x-axis, similar to what we saw before. And in this case, again, I have two possible outcomes, as we talked about it previously. So now I'm starting with the 0 state, I'm measuring along the z basis, which I get plus or minus. So I get the plus state with 50% probability, and the minus state with, again, 50% probability, right? And now I toss all the minus states again. I throw them out, and I measure along the z basis again. And if we could have the pole again, that would be amazing. So if I measure, now that we have these tools, if I measure along the z-axis, what do I expect to get? And maybe let's think about it for 30 seconds. We launch the poll. Again, up is the 0 state, down is the 1 state, and 50-50 is 50% up, 50% down when I measure. Okay, let's take another 10 seconds and then I can do the big reveal, although you guys already know the answer. Okay, I'm going to end the poll now. So yeah, what we end up with is, as a lot of you indicated, the overwhelming majority is we get 0 with 50% probability and 1 with 50% probability. And of course, the reason, the mathematical reason behind that is that at this point, when I measure the plus state along the 0 axis, the probability of measuring 0 is the overlap between 0 and plus squared. And we've seen that this is 1/2. And the probability of measuring a 1 state is the overlap between 1 and the plus state. And we have also shown this to be 1/2. And that's why I end up with 50% of the times up, 50% of the times down. So we can see that we can, using the quantum mechanical tools that we've learned from the first semester, we can explain the weirdness that's happening right now, the quantum weirdness that we saw in the CERN-Gerlach experiment. And hopefully you guys, again, find that as exciting as I do. So far, we know what two-level systems are now and why we use them. We know electron spin is a two-level system similar to a qubit. So qubits and electron spins behave the same way when we measure them. We know how to measure electron spin in different bases. And again, that extends to measuring a qubit in different bases. We will talk about that more extensively in the following lectures, but I'm just trying to give you guys motivation for why we're talking about electron spins and the CERN-Gerlach experiment. Because it's the same physics and it's just a nice intuitive picture to have when we talk about quantum bits in quantum computing. And next, we will see an interesting property that two-level systems, and again, our qubits abide by, and that's entanglement. So with that, let's take a 10-minute break, and then we'll come back.
Ready, Amir? Should we start with questions?
Yeah, let's get started with some questions.
Okay, cool. Let's start with kind of the most basic one, but just to make sure everyone's comfortable with what we're talking about, can you quickly remind us what is a quantum electron and what causes spin?
Okay, so quantum electron is just an electron. If you guys remember from the previous lecture, electrons are quantum objects. They exhibit wave-particle duality, and they abide by the laws of quantum mechanics. So the reason why there was a quantum electron in one of the previous slides, it was just to emphasize the quantum nature of electrons rather than the classical particle picture that we're used to. And what causes spin? Who knows? It's like that is an unanswered question in physics. I guess that's just how the universe is in a sense.
Cool. All right, let's jump into, is the Stern-Gerlach experiment like a Hadamard gate?
No. So a Hadamard gate is a quantum gate, right? And it's a unitary operation that doesn't destroy any information and is reversible. Whereas the act of measurement is not a unitary action. So once you measure a state of a qubit and you get a 0 or a 1, then you can't reconstruct back what the superposition was. Because all you know is that, hey, after the measurement, the qubits are either 0 or 1, and there's no way to reverse time back, or no operation that you could use to reverse back and go from like this 0 or 1 to the superposition that you were measuring initially.
Okay, so another question about measurement. Is information lost when you take a measurement?
So by definition, yes, because again, as I mentioned, measurement is not a unitary process, so it's not reversible. Again, just to reemphasize, if I tell you the outcome of a measurement, you can't tell me what the quantum state was before I measured it. And by that virtue, since it's not reversible, there is some information lost.
Cool. Also on Stern-Gerlach, so what exactly happens to the electrons inside the Stern-Gerlach magnets?
Who knows? I mean, I guess one intuitive answer that I can think of is, so the electron starts getting pulled up or down inside the magnet. So in a sense, while the electron's passing the magnet, we're slowly measuring its state of it, like step by step, the spin, like step by step. So what I can think of is the electron passing through the magnet is essentially something measuring it. And I mean, no one, like, it's hard to probe what happens inside the magnet experimentally, but if you cut your magnet in half, the outcome is still going to be the same. Your electron is still either going to go all the way up or all the way down. Now, of course, if you only have half a magnet, the electron, or the spin in this case, let me say, not the electron, because the electron also has an electric field or has a charge which interacts with a magnetic field. So let's ignore an electron and just stick with a spin. So the thing is, like, if you cut your magnet in half, your spin will still go up or down. But now it only experiences half the force because the length of your magnet is cut in half. So it only goes half as high or half as down. So essentially, the shorter your magnet is, the smaller contrast you're going to have in your experiment.
Okay. So this question is also related to kind of the outcome of Stern-Gerlach. Is the outcome of Stern-Gerlach always 50-50? And what if you measured along Z consecutively?
Yeah, that's a great question. Actually, let me launch a poll for that. I want to hear everyone's thoughts on this. So if I measure, let's say, okay, guys, before you start answering, let me state the question. So if I have this SG along Z, and I send an equal superposition in an unknown state, the outcomes are 0 and 1, 50-50%, right? And then I block the one state, and I send the 0 again through another SG along the z-axis. What do I expect to get? And again, when in doubt, use the fact that probability of getting the 0 is, oh, sorry, this is the wrong way. Probability of getting the 0 is just the overlap of 0 with psi squared, and the probability of getting a 1 is the overlap of 1 with psi, the whole thing squared. And nothing's happening between these two measurements, by the way, also let me reiterate that.
So what's the answer, Amir?
Okay, so let me end the poll. I was just waiting for more people to get in their answers. So the answer here is, again, in this case, psi is just a 0 state, right? The state that I'm sending into the second Sturm-Gerlach along the z-axis is the 0 state. So based on that, I have the overlap of 0 with 0, which is equal to 1, and the overlap of 0 with 1, 1 with 0, which is 0. So I get 0 out with 100% probability. And this is why the mathematical tools that we've discussed in this lecture and also in the previous semester are so powerful, because we can use them to essentially predict different outcomes under different circumstances. But also intuitively, if you measure and I know with quantum mechanics, you think that our intuition is completely broken, and I can't blame you. It's something that I definitely have recreated a part of my intuition, at least when I work to be compatible with quantum mechanics. But okay, with our quantum mechanics intuition now, if I measure along one axis and I get the outcome, and I measure along another axis without doing to the qubit, without doing anything to the qubit or the spin in the meanwhile, I expect to get the same thing, and that is what we're seeing. So again, if I send the 0 state directly to another Sturm-Gerlach measurement, what I end up with is 0, 100%, because 0 is the eigenstate. Again, to use a term that we've already learned, but also 0 is a valid output. So that's what I end up getting. That was a good question. Thank you.
Cool. That was the last question. So back to you.
Yeah. So let's move on to, let me see if I can, to entanglement. So in quantum entanglement is a quantum correlation between two or more objects where each of their states will depend on the state of the other. And this correlation does not depend on space or distance. So you can be on two edges of the universe and this correlation will still hold. So let's talk about an example. So we have Amir and Amin, who are cousins. They were born in the same country. They were raised together until they were children, when they were children, until one of them moved to the United States, the other one moved to the United Kingdom. And now one of them lives in Cambridge, Massachusetts, and the other one lives in Oxford. So since they grew up together, they share a form of entanglement. But now this entanglement is peculiar in the sense that whatever Amir does, it means always the opposite. So let's look at an example. So Amir and Amin go to a diner. Well, Amir, me in Cambridge, and Amin in UK, Cambridge, Massachusetts, or Amin in Oxford, UK. And of course, as is typical in Cambridge, Massachusetts or Oxford, UK, the first question that the waiter starts with is, Do you want to do theoretical quantum computing or experimental quantum computing? And again, the two parties haven't been in the same place for a very long time. So they haven't had the time to coordinate their answers. So when the waiter asks them that question, Amir, being the cooler cousin, of course, says, yeah, I do experimental quantum computing. It's amazing, it's super cool, and I get to actually do real stuff in lab. And again, without coordination, it means the exact opposite. He's like, oh, I do theoretical quantum computing because I like it better for any reason. Okay, the next question that the waiter asks is, for your dessert, do you like cookies or brownies? Again, Amir says cookies. And without any coordination, without Amin knowing what Amir ordered, Amin orders brownies, the exact opposite. Two other options. There is two different kinds of milkshakes they can have, either a vanilla milkshake or a chocolate milkshake. So Amir orders the chocolate milkshake, whereas again, Amin, without knowing what Amir ordered and being separated, by an ocean, by the Atlantic, orders the vanilla milkshake. And the final choice that they get is Pepsi or Coke. So Amir orders a Coke, and let me see if I can do the poll for this. What do you guys think, based on this entanglement that I've described, what do you think Amin orders? Pepsi or Coke? Okay, I think the results are very definitive. So Amin orders a Pepsi. Yeah, without knowing, and all these, they're different on all these questions with two answers, which should be suggestive that maybe we're talking about a two-level system because there are only two possible answers to these questions. They're different on all of these questions without knowing what the question was ahead of time. So they haven't had the time to coordinate that, if we get asked, to choose between brownies and cookies, I'm going to choose a cookie, you're going to choose a brownie. They have no idea. But since they're entangled, this entanglement, this quantum correlation will cause them to be different on any question that they get asked that has two answers. In this case, of course. I mean, there are cases of entanglement that they could have, always chosen the same thing. But in this case, they're exact opposites, and that's how they're entangled. And this is fascinating, right? Because again, if we're trying to think about this classically, for each of these questions, we need to coordinate what our answers are to always be the exact opposite on all of them. Whereas with entanglement, once you're entangled, this correlation will hold regardless of what question. And that is a fascinating thing about quantum mechanics and quantum computing. That regardless of the distance, this quantum correlation holds. Okay, with that, let's go back to the world of quantum computing. So we can show an entangled state as a superposition of two possible outcomes. So one, where qubit 1, which I'm showing in red, so I'm going to say QB1 here, is 0, and qubit 2 is a 1. And another case where qubit 1, again shown in red here, is a 1, and qubit 2 is a 0. So that is very similar to the Amin and Amir example, where their states or what they order is going to be the opposite. So if we measure qubit A, if we get that qubit A is a 0, then the state of qubit B is immediately set to 1. Because again, looking at this entangled state, the case where qubit A is 0 is this one. And in that case, qubit 1 is 1. And once we measure and find out that qubit A, or no, I say maybe we should change this to qubits A and B. I used 1 and 2 up there. But anyways, if we figure out that the first qubit is a 0, then we know immediately that the state of the second qubit has to be 1. And if we measure the first qubit to be a 1, then we're talking about this part of the superposition. And we know that the quantum state of quantum B will be immediately set to 0. Yep, that is based on entanglement. And this, this action happens immediately. So even if the two qubits are separated by the length of the universe, if I measure one, the state of the other one will immediately become determined, which is again fascinating. And in fact, I think I might have mentioned this in the first lecture, but Einstein was very uncomfortable with this concept because there's a speed limit to the universe, how fast anything can travel, and that's the speed of light. And this interaction, what I described here, happens instantaneously. So it's not really limited by any speed limit. And of course, you can't send any useful information that way. We're going to talk about this a little bit more down the line, but it is a very unintuitive concept, classically. And the idea is that this entanglement, what I'm claiming is that it's preserved under local operations. So what do I mean by a local operation? Is if I apply an operator to a single qubit. To only one of the qubits. So let's say if I start with the superposition, sorry, the entangled state that I talked about earlier, which was 0, 1 plus 1, 0 divided by square root of 2, and I apply an X gate to the first qubit. So here again, the first qubit, let me maybe use a different color for that. This is the first qubit, right? And if I apply an X gate to that, I'm flipping the value of that qubit. So what I end up with is 0. Okay, so this 0 goes to 1. So let me erase that. So the first 0 goes to 1 because X flips the state of the qubit. So I get 1, 1. And then for the second part of the superposition or entanglement, this 1 gets flipped to a 0. So we end up with 0, 0 divided by square root of 2. And for this state also, if I measure the state of the first qubit, I will immediately know the state of the second qubit. So in this case, if QB, I'm going to say A for the first qubit is 1, then QB B, or the second qubit is also 1. And if qubit A is a 0, then, okay, so if qubit A is a 0, then we're in this part of the entanglement. So then qubit B is also 1 up here, 0 down here. And the takeaway message here really is that entangled qubits will stay entangled if we only apply n operator to a single one of them. So in order, you can't really unentangle entangled qubits unless you do something more sophisticated. But if you only apply a single operator to one of them, they will still stay entangled. Now, I mean, something that's different is they went from being anti-correlated to being correlated, but they're nevertheless still entangled. And let's talk about the Bell state, something called the Bell states. And again, we're going to see this more in detail. This is just to give you an example of what entangled states actually look like. And so there are different ways that we can arrive at an entangled state. So the one entangled state that I talked about earlier is not the only possible way to entangle two qubits, to show entanglement between two qubits. So okay, it says beta, and it's not showing there. So one example is this, what we call a beta 0,0 state, which the name doesn't matter for now. That is that has 0, 0 plus 1, 1. So in this case, if the first qubit is 0, the second qubit will also be 0. If the first qubit is a 1, the second qubit will always be a 1. That's one example. Another one is, okay, again, not box, but beta. This 0, 1 plus 1, 0 state. In this case, if the first qubit is 0, the second qubit will always be a 1. And if the second qubit is a 1, the first qubit will always be a 0. And there's another one. So this is 0, 0. And again, the key is minus 1, 1. And I'm dropping the 1 divided by square root of 2, of course. But so this entangled state is very similar to the first one that we talked about, in the sense that, again, if you measure the state of the first one, you get a 0 for the value of the first qubit. The value of the second qubit will also be 0. And if you get a 1 for the value of the first qubit, the value of the second qubit will also be 0. But now there's a negative sign in between. And again, the same way that, the plus state, which again, as a reminder, it's 0 plus 1 divided by square root of 2. And the minus state, so now there's a minus sign between the two. In the same sense that these two are not the same, this beta 0, 0 is also not the same as this beta 1, 0 that we have over there. And we're going to see the properties of these states down the road when we get into quantum computing, but we just want you to get comfortable with the fact that there are multiple different ways to entangle qubits. And of course, the last one is this beta 1, 1 state, which again has this negative sign in between. So, beta 1, 1 is not the same as beta 0, 1. Although, again, the correlation seems to be the same. So both qubits are anti-correlated, meaning that if we measure the first qubit to be 0, the second qubit will always be a 1. And if we measure the first qubit to be a 1, the second qubit will always be a 0, will always be different. And again, if this seems a little bit too complicated now, don't worry about it. We're just introducing this, and you will see this down the line with more math when Fran takes over. And finally, I want to talk a little bit about applications of entanglement. So why do we care about quantum entanglement, besides the fact that it's a super cool thing, of course? So first of all, quantum entanglement has applications in quantum teleportation. And we're going to talk about quantum teleportation in one of our lectures down the road. But if any of you have seen Star Trek, you see that people or objects teleport between places. And actually that is possible based on the laws of quantum mechanics. So you can take one quantum bit of information and transfer it to somewhere else in space without actually moving the qubit itself. So you can teleport a quantum state without physically moving the qubit between, between 2 points, between like your first, between your start point and your destination. And that is super cool. That is basically something from sci-fi that you could do in lab, and actually we do in lab. Another example is quantum cryptography. So something that we discussed 2 slides ago is that entanglement is preserved under local operations. So what it translates to is that unless you have both entangled states, or you know what both the entangled states are, you can't extract anything out of it. That's a translation of that slide that I had earlier. So that makes entanglement a good candidate to be used for quantum cryptography, because in a sense you can encode your quantum message or your secret message in these different bell states that we talked about, And the only way to actually access that information is to have both of the entangled qubits and do a certain kind of measurement on them. Like you know exactly what to do with them. And if you only have one of the qubits, that is actually 100% safe. So if you use quantum entanglement and you only have one of the qubits, there's no way to find out what the secret message is. You need both. And of course, an application of that is super dense coding, which is something that we will talk about again later on in the class. But the idea of super dense coding is that you can send 2 bits of classical information by only transferring 1 qubit. So if you and another party share an entangled state, you can do some operation on your qubit, your part of the entanglement, and send it over to your friends. And by sending that 1 qubit over, you can get 2 classical bits of information across. And again, it is secure because if someone steals your qubit, they're still not going to know what the message was, since they don't have access to your friend's qubit, the other half of the entanglement. And the final thing, of course, is quantum speedups. So entanglement, these quantum correlations or quantum algorithms and quantum circuits plays a big part in getting quantum speedups. And again, if you guys remember, just to review back to what we discussed the previous lecture and also throughout the course, is that there are 3 resources available at our disposal to use a quantum computer to gain an advantage over classical computers. So we've talked about superposition extensively. We talked about quantum interference in the context of wave-particle duality and how every particle, including our qubits, exhibit wave-like behavior, which means that they would be able to interfere with themselves or the state of the other qubits, essentially doing quantum interference that way. And the final piece of the puzzle is quantum entanglement, which we talked about. And using these 3 resources, quantum algorithms can gain an advantage over classical algorithms that we're used to. And with that brings us to the end of this lecture. I would love to stick around and answer a few more questions, Rachel, if you guys see anything in the chat. But yeah, that was it for the material I had.
We have a few more. Actually, we'll jump in with some of the common questions.
Yeah, so I mean, you're probably expecting this question, but a lot of people wanted to know if you can use entanglement to send information faster than the speed of light.
That's an amazing question. So actually, no. And that's why entanglement, that's why this form of quantum correlation is possible in the universe that we live in. Because as I mentioned earlier, there's a speed limit to how fast anything, including information, can travel, and that's the speed of light. So now the idea is that, going back to our entangled example, right? So maybe going back to this example that we have. So if I measure qubit A and I get a 0, then that way I can immediately set the state of qubit B to 1. But now the problem is that this is random, right? Because I get, again, if I only measure qubit A, I get that it's 0 with 50% probability and 1 with 50% probability. So there's no control weight for me to use the entangled pair of qubits that I have to send a meaningful message. Because every time I use this spooky action at a distance, when I measure one and then the state of the other one becomes immediately determined, it's 50-50 if it's 0 or 1. So since it's completely random, there's no way to actually meaningfully send information faster than the speed of light that way. And even when we talk about quantum teleportation, something that I didn't tell you is that in order to do quantum teleportation, you need to send 2 bits of classical information over. So for quantum teleportation, you have the state that you want to teleport, the state of the qubit that you want to teleport, and an entangled pair. And let's say, going back to the Amin and Amir example, let's say Amin wants to teleport a state to Amir, and they share an entangled pair. So Amin, in Oxford, our names are kind of similar, so let me draw that distinction. So the dude in Oxford, who's Amin, will do an operation, will do something, again, and we will discuss what this something is later in the course. We'll do something to the qubit that he's trying to teleport and the entangled pair that he has, and sends over 2 classical bits of information. Now, sending over classical bits of information, that for a fact is limited by the speed of light. And then based on those 2 classical bits of information, Amir, the guy in Cambridge, Massachusetts, will know what to do with his part of the entanglement to essentially get the state that Amin was trying to teleport to him. Again, hopefully that gets you guys excited for when we talk about quantum circuits and applications, including quantum teleportation.
Well, another common question was, how do you create entanglement, and also how do you break it?
That's a great question. So we are going to talk about how to create entanglement using quantum circuits in, I want to say, 3 lectures, like when we talk about quantum circuits. And we're going to talk about how to unentangle them also using quantum circuits in the same lecture sequence. But one thing that I can tell you, again, from a purely physics perspective and not necessarily quantum computing, granted it does apply to quantum computing, is particles become entangled when they interact a lot with one another. And again, you can think back to the example of Amin and Amir, right? They grew up together for a portion of their lives, and that interaction made them somewhat entangled, such that they're always anti-correlated to one another. So actually, maybe Akshay, you could also chime in on this. So I know you guys do a good bit of entanglement in your lab as well. And I know you guys entangle electrons, if I'm not mistaken. How do you do that?
Well, actually, that's the dream. We haven't actually entangled any electrons yet.
Okay, what's the proposal for it?
So what we try to do is energy entanglement. So we want to entangle electrons in energy. And the idea is that you basically shoot electrons at a material, or you shoot them very close to a material. And then with some probability, the electron is going to excite some some excitations inside the material. And then if the electron does make that excitation, then the electron loses a little bit of energy to do that excitation. And then what we hope is that you have that entanglement between the state where the electron has a lower energy and there is an excitation, or the state where there is no excitation and the electron has the same energy as it started off with. So that's how we want to do it. We are currently looking for money to do it. So if anyone in the call has a few $1 million lying around.
Yeah, so I mean, the point that I was trying to get across is that there are many different ways to entangle quantum objects in lab. In quantum computing, we do them using a Hadamard and a CNOT. And again, I'm not going to go into detail right now, but that's something that we see. But in general, some form of interaction between particles often causes entanglement.
Well, and then another question was, can you entangle more than 2 qubits or more than 2 electrons?
That's a great question. So let's talk about qubits, because it's much easier to talk about qubit entanglement than electron entanglement. So the answer is yes, although you can only have 2 qubits be fully entangled with one another at the same time. And that notion is called the monogamy of entanglement, meaning that full entanglement, you can only have 2. Of course, you can have three qubits that are partially entangled with one another, but no pair in that partial entanglement is completely entangled. Now, what I mean by complete entanglement, that is a bit of an open topic of research, and also has a little bit of a mathy definition. But in a sense, you can't describe, like, they won't be as strongly correlated, rather, let me put it that way. If you have 3 particles entangled, which you can totally do, like no pair in that 3 particle configuration can be as strongly entangled or as strongly correlated as the scenario where you only have 2 qubits or 2 particles entangled.
And then another question was, so this is going back to the Stone-Gerlach experiment.
Mhm.
Is it somehow related to the uncertainty principle?
Actually, yes. Well, rather, the uncertainty principle uh, comes from I mean, I'm trying to use words that won't get me in trouble with too much math. But yes, it is related. And actually, if you think about it, you can think of position and momentum as somewhat different axes of measuring an object. The same way that the Stern-Gerlach along X is different than the Stern-Gerlach along Z. So it's the same physics. And the fact that once you measure one, you lose information about the other one is actually what leads to the uncertainty principle. So in a sense, going back to this part of the story, there is an uncertainty principle between measuring along the z-axis and measuring along the x-axis. So if I know exactly what the value of the spin is of a qubit or an electron spin is along one axis, I have no clue what it is along the other axis, and vice versa. Similar to the uncertainty principle.
Well, and then another kind of question some people had was, can you go back to that analogy that you had drawn about color and shape of an object, and
Yes.
like maybe go through that once again?
Yeah, sure. So the idea here, and again, this is a classical analogy, and the point is to show that what we talked about with spins sounds absurd and unintuitive in the classical world that we live in. So the idea here was that an object, let's say it has two properties in a simplistic world. One of them is color, and it can either be red or blue, and the other property is shape. It could either be square or a circle. Now, if I measure the shape of an object, and I get, and I essentially dump all the objects, throw out all the objects that are squares, and then I measure the color of an object, which again can either be red or blue, let's say with 50% probability each, and I throw away all the objects that are blue. Classically, what I expect is to only be left with red circles, right? Because after measuring the shape and the color, I threw away everything that was a square or blue. So I'm only left with red circles. But now in the quantum world, after I measure the shape or look at the shape of the objects again, after like only keeping the red circles, or classically at least keeping the red circles, what I see in the quantum world with spins is that I actually end up getting still circles with 50% probability and squares with 50% probability. And of course, that is surprising, right? Because just thinking about it in our day-to-day lives, once we throw out all the squares, like all the objects that are squares, there's no way that we're going to end up with like more squares if we look at the color. If we look at the color of the object. But here again, by looking at the color of the object or the spin, in this case, let's just stick with spin now. By looking at the color of the spin, we lost all information about its shape. And that's how we ended up, being in a 50-50 superposition of different shapes.
So if you measured shape once and then say you got circle, and then you measured shape again, what would you get in that case?
Okay, this part actually follows the classical intuition. So you'll get circles again. So as long as you don't measure color or do anything to your circles in between your shape measurements, you'll always get the same shape. And in that sense, that part is consistent with the intuition that we have.
So it's when the other
Now,
properties
the unintuitive
measured.
part, sorry?
So I was just saying, so it's when the other properties measured that the first one gets messed up.
Exactly, yeah. And of course, if we're talking about it in a quantum mechanical context, it's a little bit more subtle. There are certain properties that you can measure that won't mess up the first property that you measured, but for measurement along different axes, those are measurements that will mess up with the properties of the previous measurements.
And then I think one last, not really question, but I guess a lot of people want to know more about like cryptography and entanglement. So maybe could you give us like an overview of what we'll be doing over the rest of the semester?
Yeah, absolutely. So again, if you guys are excited and interested about cryptography and teleportation and the things that we discussed in these last slides, once we start talking about quantum computing, you'll have a lot of fun. Because again, you're going to see that we're using quantum computing and quantum mechanics, and we can do things that seem like they're out of sci-fi, but that's actually, you can actually accomplish that with physics, which is amazing. So now for cryptography, quantum cryptography specifically, we can either use entanglement to encrypt our message. And again, with entanglement, really, unless you have both pairs of the entangled qubits, there's no way they can extract any useful information. So it's very secure in that sense. But now one technologically challenging aspect is generating entanglement over long distances is difficult. That is a technology that's being developed today, and it's still an active work of research. Now, there's another cryptography proposal. I mean, actually, there are a whole bunch more, but like another one that falls under the same general family of let's encode information, quantum information, or the information that we're trying to send away in different bases. So let's say my bases are again along the z-axis or the z bases or the x bases along the x-axis. Now, if I encode a 0 in the z basis and I measure along the x basis, what do I end up with? And maybe actually for that, let me dust off the poll again and see what you guys think. So I'm preparing, okay, let's say up is 0, down is 1, and 50-50 is 50-50. So I prepare a 0 in the z basis and I measure along the x basis. Actually, in this case, up will be plus, down will be minus, and 50-50. I mean, something that I'm seeing already is that the majority of the people are saying 50-50, which is correct. So if there's a bad actor in between that wants to access your information, but doesn't know what basis you've prepared your qubit in, then chances are, with some probability, they're going to guess the wrong basis. And based on that, they're going to get totally random information. They're going to get essentially, 50% 0, 50% 1, which is no information whatsoever. And in that sense, you can use this weird behavior of spins to our advantage to at least send a shared key of some sort, like send some message, encode some message such that it's secure from a third party that doesn't know what basis you're using to prepare this. So they measured in the wrong basis. Yeah, we're going to talk about this more. So that protocol is, of course, it's not entanglement based, but it's called BB84. For those of you who are interested, and that's QKD, quantum key distribution. We're going to see this down the line in the course. But also that's another application of this spin-like properties and these measurements that we talked about with the CERN-Gerlach experiment.
I think that's all of the common questions that people had.
Yeah, Rachel, do you have any announcements?
Nope, I think that's it. You can wrap us up.
Okay, amazing. Well, thank you guys for sticking around. I hope you enjoyed this lecture. And to foreshadow, next week we're going to talk about the postulates of quantum mechanics and actually how do all these concepts that we've talked about so far fall under the same umbrella that then we can use for quantum computing. So yeah, with that, again, thanks everyone. Have a good rest of your weekend.